Hello everyone, my name is Rohit Gowri Shetty and I'm here to talk about on a topic called Polygon Rendering. Let's start the presentation. What is Polygon Rendering? Polygon rendering is a method of creating two-dimensional images corresponding to the three-dimensional objects in the real world. These three-dimensional objects are made up of polygons. Any shape can be approximated using polygons. The set of algorithms which produces the image are collectively known as rendering pipeline. Most 3D graphic applications use polygon rendering pipeline to generate images corresponding to the 3D objects. Now we have got the idea of what is polygon rendering. In the polygon rendering, we have three types of shading. One is flat shading. First one is flat shading. What is flat shading? Flat shading, as I said, each object in a real world can be made to an 2D image using polygons. Here in the flat shading, only single intensity is allocated to each polygon. It is very fast and simple method. It gives reasonable results as it is very fast and easy to implement. The objects here are polyhedrons and the light source is far away from the surface, so that n dot l is constant over each and every polygon. That is, the every intensity is evenly distributed over the entire polygon. The viewing position of to the object is also very far, so that v dot r is also constant. So how it works? As I said, it works by applying a single pixel color to the entire polygon. It is very quick and efficient, but the realism is limited. What that means when the 2D image is out, it is not exactly matching to the 3D object because every polygon is different. The entire polygon has a same color, and the separation between the polygons is clearly visible. Next is Garand shading. What is Garand shading? Garand shading, what it does is, what is the difference between Garand and the polygon shading? Flat shading, sorry. In contrast to flat shading, with smooth shading, the color changes from pixel to pixel. It assumes that the surfaces are curved and uses interpolation techniques to calculate the values of pixel between the vertices of polygons. That is, near the vertices of the polygons, averaging is done and linearly interpolated to get the value. That means there is no differentiation between the edges of the polygon. As I said, averaging the normal vectors for each polygon sharing that vertex. That is, average is taken with all the normal vectors, so that there is no differentiation between the vertices. It is an interpolation method used in computer graphics to produce continuous shading of surfaces representing any polygon meshes. Computing the lighting at the corners of each triangle and linearly interpolating the resulting colors for each pixel covered by the polygon. Here I show the difference between the flat and Garand shading. As I said, in the flat shading, every polygon can be differentiated as there is a difference of color between each polygon. In the Garand shading, averaging is done along the vertices, so you cannot easily differentiate with the vertices. The next is Phong shading. This method was named after the make by Phong Boi Tiong in the University of Utah. A more accurate method for rendering polygon is to interpolate normal vectors and then apply the illumination model to each surface point. Fong shading improves upon Garn shading and provides a better approximation of the shading of a smooth surface. The most serious problem with the Garn shading occurs when the specular highlights are found in the middle of a large polygon. As I said, the interpolation is done only at the vertices. What if a specular highlight is entirely inside a larger polygon? Since specular highlights are inside the polygon, Garn shading interpolates based on the vertex color, so it doesn't give a effective one because the specular highlights are missing. This problem is fixed by the Fong shading. What is the algorithm of the Fong shading? Determine the normal at each vertex, linearly interpolate the vertex normal over the surface polygons, apply the illumination model along each scan line to calculate intensity of each surface point. As I said, definitely there should be some trade-off between the Fong shading and the Garn shading. We accept that Fong shading is better than Garn shading, but it comes with some trade-offs. What are the trade-offs? It is much slower than Garn shading, and the implementation is very high in Fong shading. However, there are fast Fong surfaces rendering approaches that can be implemented iteratively. Typically, Fong shading is implemented as a part of a visible surface detection technique. Here is the difference between the flat Fong and Garn shading. The top right is flat shading. As you can see, there is a differentiation between the vertices, and then the bottom left is a Garn shading, and where the color between in the entire polygons is missing, where in the Fong shading we can easily get the differences because it is effectively implemented. Next is match band effect. Match band is an optical illusion named after the physicist Ernst Mach. What is match band effect? Match band effect is nothing but it exaggerates the contrast between the edges of slightly differing shades of grey as soon as they come to contact one another by triggering edge detection in the human eye visual system. That is, the darker becomes much darker and the lighter becomes much lighter. In that sense, it doesn't become much lighter. It is only our illusion, our eye takes that. So these are the shading effects in the polygon rendering. Next, we'll go for visual surface detection. What is visual surface detection? When we view a picture containing non-transparent objects and surfaces, then we see those objects from view which are behind from objects closer to the eye. We must remove all the hidden surfaces to get a realistic screen image. The identification and removal of those surfaces is called hidden surface problem. So what is correct visibility? When multiple opaque polygons cover the same screen space, only the closest one is visible. That is called a correct visibility. A set of 3D surfaces are to be projected on the 2D screen. That is known as polygon rendering, as I said, to identify those parts of the scene that are visible from the chosen viewing point. Only the objects which are closer to me should be visible rather than the hidden surfaces to get a realistic sense. There are many algorithms working in this area and still is in research. Characteristics of approaches. There are many approaches, but there are some they lag one point and they have better efficiency at other point. They are request large memory, request high processing time, applicable to which type of objects. Some require large memory, some require high processing time, and some require both large memory and high processing time, and some are applicable to only some type of objects. Visual surface detection algorithms are broadly divided into two categories: object space method and image space method. What is object space method? Decided which object has a hole is visible. Here, only the approach is based on the whole object. In the image space method, the visibility decided by point to point, that is, it is calculated by pixel wise. Most visible surface algorithms are image space algorithms. At times, they are also called as hidden surface elimination. So, in our presentation, we're going to discuss about all these algorithms one by one. First is backface removal, and the second is depth buffer. Third, A buffer. A buffer is an extension depth buffer, and the skyline algorithm, depth sorting, BSP trees, binary search partition trees, area subdivision, octrays, and the final is raycasting. So first we're gonna discuss about backface removal. What is backface removal? Backface removal is nothing but first detect what is a back object or backface and remove that. That's it. A fast and simple object space method for identifying the back faces of a polyhedron is based on the inside out test. A point x comma y comma z is inside a polygon if let's say the plane has a comma b comma c comma d as its plane parameters, then it is inside a polygon if ax plus by plus cz plus d is less than 0, then it said the point is inside a polygon. When an inside point is along the line of sight to the surface, then the polygon surface should be backface. I'll explain this clearly with an example in the later slides. Backface removal. A simple and fast object space method finds the backs of the polygon and discards them as a set. Backface test by considering the direction of the normal vectors for the polygon surfaces. The polygon surface is backspace when v dot n greater than 0. Here v is a view direction and n is a normal vector to the surface. If they are in the same direction, then it is definitely a backface. Then it is greater than 0. Here is an example. Backface. As you can see, view is a view direction of a camera lens, and n is a backside of a cube where the normal vector is perpendicular to the surface. So n is in the left direction. As v is also in the left direction, dot product of these two vectors is definitely greater than 0. Then it is decided that it is a backface, and we're going to eliminate that. And also we can also not see the surface with a surface that has c equal to 0. Therefore, we can identify polygon surface as a backface if c is less than or equal to 0. So next method is depth buffer method. Here depths are calculated and the object which is nearer to the point of view is only taken into consideration. This method is developed by CutMove. It is the image space approach. The basic idea is to test the depth of each surface to determine the closest surface. Compare surface depth values throughout a scene for each pixel position on a projection plane. Usually applied to scenes only containing polygons. Surfaces can be processed in any order. To override a closer polygon with the farthest one, two buffers are used in these algorithms. They are frame buffer and a depth buffer. Depth buffer is used to store depth values for xy position as surfaces are processed. The frame buffer is used to store the intensity value of that pixel at that position xy. Here xy means at that pixel. How the algorithm runs. Initialize the depth buffer and the frame buffer so that all buffer positions x comma y. Like initialize depth buffer with 1 and the frame buffer as BG color, background color. Process each polygon in a scene one at a time. For each projected x comma y pixel position of a polygon, calculate the depth set if not already known. Here how to calculate the depth I'll show in the later slides. If z is less than depth buffer x comma y, compute the surface color at that position and set depth buffer equal to z and frame buffer equal to surf color x comma y. After all surfaces are processed, depth buffer and frame buffer will store correct value. So here's a calculation for z. As I said, ax plus by plus cz plus d equal to 0 is the equation for a surface of an object. Then calculating z is like transferring everything to the right position, we get z. Other way is using incremental calculation. The depth of the position x comma y equals to z is increment the x value or increment the y value. Anyways, we here by doing that we'll get the next depth of a next position, or we can use using interpolation. What are the pros of cons of this algorithm? It can be easily implemented in the hardware, no sorting of surfaces is needed. What this means, in the later algorithms we will use sorting of the depths. So here is a plus point for that, because there is no sorting. It processes one object at a time. What are the cons? It requires large memory, it is very time consuming, difficult to deal with transparent objects, because it deals only with polygons. The next algorithm, accumulation buffer. As I said, accumulation buffer is an extension to the depth buffer method. A buffer expands on the depth buffer method to allow transparencies. Here transparencies are allowed, where in the depth buffer there is no transparencies are allowed. The key data structure in the A buffer is the accumulation buffer. Each position in the A buffer has two fields. Depth field, it stores some positive or negative numbers. Intensity fields, it stores some surface intensity information, that is the color value at that pixel. Depth buffer method only identifies one visible surface at a time, but here it accumulates color values for more than one transparent and translucent surfaces. The algorithm is as follows. When drawing a pixel, if polygon is opaque and covers pixel, then insert into the list and remove all the polygons farther away and fill that pixel with that object nearer to it. If the object is transparent, then we need to store all the values of the objects which are transparent below. As I said, if the depth value is greater than 0, then the number is stored at the position in single surface overlapping the corresponding pixel area. It then stores the RGB component in that intensity field and also the percentage of pixel coverage. If depth is less than 0, and then it stores the information about the multiple surfaces which contributes to pixel intensity. The intensity field is linked lists connecting surface information values, which includes RGB components, opacity parameters, depth, percentage of area coverage, surface area, etc. Here the color intensity of the pixel depends upon all the values in different depths. What are the pros in that? Here, as we saw, more than one surface area is covered. There's definitely a pro. Transparent objects are allowed here. Coverage mask idea can be used in other visibility algorithms. What are the cons? Very slow when running in software, having problems of over rendering and depth quantization problem. But it is widely used in high quality rendering tools. The next algorithm is scanline method. It is an image space method for identifying the visible surfaces. It is also other image space method. What it does is compares and computes the depth values along various scan lines for a scene. What it does is for every scan line, it takes the intersection edges, intersection points, and computes the depth for each scan line incrementally. If you require to get depth values for one scanline, we should group and process all polygons intersecting that scanline at that time. How the algorithm works? Here, two important tables are maintained. The edge table, it contains coordinates endpoints of each line in the scene and inverse slope of each line and pointers into the polygon table to connect edges to surfaces. And the polygon table, it contains the plane coefficients, surface material property and other surface data and maybe pointers to edge tables. To facilitate the search for surface crossing a given scanline, an active list of edges is formed for each scanline as it is processed. This active list stores only those edges that cross the scanline in order of increasing x. And also a flag is set for each surface to indicate whether a position along a scan line is either inside or outside the surface. Pixel positions across each scan line are processed from left to right. At the left intersection with the surface, a surface flag is turned on, and at the right intersection, the flag is turned off. We only need to perform depth calculation when more than one surface has its flag turned on at a certain scan line position. As you can see, if there is a scan line and at the starting we are setting a flag on and the starting we are setting a flag off, so when there is an only intersection we get a scan flag on, surface flag on and off if there are if two surfaces are intersecting, then we can know that the surfaces are intersecting, and we can calculate the depth, which is depth to differentiate between the surfaces which are above and below. Here is an example. As you can see the line, line 3 flag is set on and off. So we can definitely come to conclusion that there is an intersection of the surfaces. By the calculation we can determine that which is above and which is below, and the below surface can be removed. The next is depth sort algorithms. A fairly simple visible surface determination algorithm is based on the principle of painting objects from back to front. It is also called as painter's algorithm because that more distant polygons are overwritten by a closer polygon. Sort all polygons according to their increasing distance from the viewpoint and then scan them in a reverse order. Sort all the polygons according to increasing distance from the viewpoint and then scan them in a reverse order back to front. This step sort is sometimes called a painter's algorithm because it mimics the way that oil painters usually work. The algorithm is very simple. Sort all algorithm based on the farthest z coordinates, resolve ambiguities if there are any. What are the ambiguities? I'll just discuss in the next slides. Draw the polygons in order from back to front. First we must determine what is z extent of each polygon. What is z extent means the minimum and maximum coordinates, minimum and maximum value of the set is z extent. Difference between the minimum and maximum. The difference between the minimum and maximum of the z coordinate is called z extent. When the ambiguities arise, when the minimum of, as you can see here, the minimum of surface 1 and the difference between the coordinates between the minimum and maximum of surface 1 has included the minimum maximum of the surface 2. Here ambiguities arise. The minimum maximum of the z coordinates correspond to this image. So there is some intersection of the surfaces. How to resolve that? All polygons whose z extents overlap must be tested against each other. We start with the furthest polygon, call it P. Polygon P must be compared with every polygon Q whose z extent overlaps P's z extent. 5 comparisons are made. Like there are 5 rules to be compared. If at least one comparison is true for each of the Q's, then P is drawn and the next polygon from the back is chosen as a new P. If none of the comparisons is true, then they are swapped and the process is repeated. What are the 5 rules? Do P and Q's extents not overlap? Do P and Q's y extents not overlap? Is P entirely on the opposite side of Q's plane from the viewpoint? Is Q on the same side of P's plane as a viewpoint? Do the projections of P and Q onto the xy plane not overlap? If these all 5 tests fail, then switching P and Q will work. Test 1, 2 and 5 does not differentiate between P and Q because there is no much difference between P and Q. But 3 and 4 do. So we rewrite 3 and 4 as: is Q entirely on the opposite side of P's plane from the viewpoint? Is P entirely on the same side of Q's plane as a viewpoint? If all this test fail, then we split either P or Q using the plane of the other. The new cut polygons are inserted into depth order and the process continues again from the starting. The next algorithm is BSPG, binary search partition trees. What it does is it partitions the space into a binary tree and searches from back to front. Tree splits 3D world into planes. The world is broken into convex cells. Each cell is an intersection of the half spaces of splitting planes of tree part to the cell. Splitting planes can be arbitrarily oriented. Choosing a splitting polygon. Split its cells using the plane on which the splitting polygon lies. May have to chop polygons into. Continue until each cell contains only one polygon fragment or one single object. Here is an example for BSP trees. Here the space is divided first, but the primary space is divided by A into two sides, and in the left side of the A there is again a partition with C. Here the plus and minus indicate that plus has an object in that direction, and also as you can see there is also differentiation B. So A is a root node and 3, 2, 4, 1 are the objects. By the final decision of this tree, we have all the objects in the leaf nodes. Area subdivision algorithm. It is also an image space method. It takes advantages of area coherence in a scene by locating those view areas that represent part of single surface. The total viewing area is successfully divided into smaller and smaller rectangles until each small area is simple. That is, it has a single pixel, or it is covered wholly by a part of a single visible surface or no surface at all. The procedure to determine whether we should subdivide an area into smaller rectangle is, we first classify each of the surfaces according to the relationship with the area. What is surrounding surface? Is a single surface completely encloses the area. What is overlapping surface? A single surface that is partly inside and partly outside the area. Inside surface, a single surface that is completely inside the area. Outside surface, a single surface that is completely outside the area. Here is an example: surrounding surface, an overlapping surface which is part in the inside area and part of inside surface. The entire object is inside the surface. Entire object outside the surface called outside area. To improve the speed of the classification, we can make use of bounding rectangles of surface for early confirmation or rejection that the surface should be belong to that type or not. How it does? Like if a rectangle has no object at all, then classification of that region is useless. So we can make an early decisions to avoid that. Check the result from 1, that if any of the condition is true. If it is not, then no subdivision of the area is needed to avoid unnecessary calculations. The next is octree method. Similar to the area subdivision, when an octree representation is used, visibility testing is done by searching octree nodes in front to back order. In the example below, what are the front octanes from the viewing point? It should be 0, 1, 2 and 3 are visible, and 5, 6, 4, 5, 6, 7 are hidden by the front. When a color value is encountered, it is saved only if no previous values are saved. What does that means? First, the preference is given to the front divisions. If there is no color in that division, then only the object color in the rear octanes are applied to that. As I said, only front colors are saved. Visibility testing is carried out with recursive processing of octree nodes and create quadrate representation. Depth first traversal of an octree. Octree 0 is visited before. Completely obscure nodes are not traversed. Different views of objects octanes are renumerated so that 0, 1, 2, 3 are front nodes. As you can see, there is subdivisions between the octants too. These subdivisions occurs until there is each object or single pixel has a uniform intensity. The next topic is ray casting methods. What is ray casting? Raycasting is a use of ray surface interaction intersection tests to solve a variety of problems in computer graphics and computational geometry. Here, the intensity of a pixel in an image is due to the ray of light having been reflected from some objects in the scene, pierced through the center of the pixel. As you can see, as you have learned from your childhood that the color of an object is because of the reflection of light by that object. So visibility of surfaces can be determined by tracing a ray of light from the center of projection to object in the scene. Find out which objects the ray of light intersects. Then determine which one of these objects is closer to the viewer. Then set the pixel color to that object. If they're like in a scene, there are like 10 tens of objects, then the object which is closer to the viewer, the color is applied to that corresponding pixel. One of the approach is space partition approach. How does it does? It partitions the space into a regular grid of equal size volumes. Each volume is associated with a list of objects which are contained within or intersects the volume. Yeah, there is a proper possibility that the object can be intersected, that is object is in both the partitions. Intersection calculation is only applied to those objects that are contained within the partition through which the rays pass. Objects lying within the partition which do not intersect with the rays are not processed. Next is the wireframe method. In the wireframe method, the first thing is to apply depth queuing as it's an initial processing. Displayed intensity of line is a function of its distance from the viewer. Hidden edges are eliminated or displayed differently from the visible edges. Methods are also called visible line detection method or hidden line detection methods. What is an algorithm? Compare edge positions with the positions of the surface in a scene. Same methods used in line clipping algorithms. Compare edge and surface depth values. If both projected edges endpoints are behind the surface, the edge is hidden because it is not necessary to be projected. Calculate intersection positions and depth, determine the depth values at that intersection position. Wireframe method is nothing but for an object, uh, a structure with sorry a wireframe method. What it does exactly is, if I have an object, if that object can be constructed with a single wire, imagination that a object is created with just a wire. As I said, first is an like a robo has an image, has an structure in the first figure, and the back lines cannot the back lines are not necessary, so that they are hidden, and the front lines with the different shades can be differentiated. The next is ray tracing. In computer graphics, ray tracing is a technique for generating an image by tracing the path of light through pixels in an image plane and simulating the effects of its encounters with virtual objects. By analyzing the real objects and like the shadows and everything, it can be virtualized into an imaginary object. This is the ray tracing is an important phenomenon of today's uh, real experienced enhanced modern games. A very simple method to both understand and implement. It is based on the idea that you can model reflection and refraction by recursively following the path that light takes as it bounces through an environment. As you can see, the image of a 3D object is captured by the camera. The light rays falls on the object. That color is reflected back. that is captured, and the shadow of that object is also captured. Ray tracing implementation. Ray tracing breaks down into two tasks: constructing the ray to cast intersection rays with the geometry, and uh, correspond and filling the corresponding pixels. The former problem is simple vector arithmetic. Intersection calculation can be done in the world coordinates or model coordinates. Constructing rays. Define rays by the initial point in the direction x of t equal to x naught plus td. As it is a straight line x naught plus t. I rays from the eye through a pixel. Rays coming from the eyes are called iris, constructing using the eye location and the pixel location on the image plane. Shadow rays from a point on a surface to the light. What are reflection rays? Rays from a point on a surface in the reflection direction. Transmitted rays from a point on the transparent surface through the surface. Aim. Find the parameter value ti at which the ray first meets object I. Write the surface of the object implicitly, f of x equal to 0. Unit sphere at the origin is, the equation of the unit sphere at the origin is x into x minus 1 equal to 0. Plane with normal and passing through the origin is n dot x equals to 0. As you can see, plane with normal, and the normal is perpendicular to the surface, so n dot x equal to 0. Put the ray equation in for x. Result is an equation of the form f of t equal to 0 where we want t. No, it's just a root finding. Ray x of t equal to x naught plus td, and the equation of sphere is x into x minus 1 equal to 0. Substitute x naught plus td in the sphere equation. We'll get an equation like d dot d into t square plus 2 into x naught dot d into t plus x naught dot x naught minus 1 equal to 0. Like, it can have two solutions. When a ray passes through the sphere, it has two intersection points, or it can have one position. When a ray is tangent to the sphere, then it has only one position, or it can also have zero solution when the ray does not intersect the sphere. Here numerical stability is very important. For example, can a reflection ray hit the same sphere again, so that it can have many intersections? It is a very important issue. As I said, in this figure, the sphere is defined its center S and its radius r. The intersection of a ray with a sphere can be computed as follows. The I is a point of viewpoint. Dx is a direction of the ray. So C corresponds to S minus I. V is nothing but view. Dx cap into C cap. Here B square equal to C square minus C dot C minus V square, following the Pythagoras algorithm. Then we can get T equals to V minus R square minus P square. R square minus B square is equals to 0 when the ray is tangent to the sphere, so that R equals B. Next is a ray plane interaction. X of t equal to x naught plus td, and the plane has a normal n, so that n dot x equals to 0. Substitute it ray equation in the plane equation, so we'll get n dot x naught plus td equals to 0. So we'll get t as minus n dot x naught by n dot d. This is plane going to origin. What about the arbitrary plane? To do polygons intersect with planes, then do point in polygon test. Ray tree. As I said, every ray has a reflected ray, every ray has a reflected ray, transmitted ray. So ray tree is nothing but drawing a tree structure with the reflected, transmitted, and the lightning rays. As you can see from the viewpoint, L1 is a lightning ray. Then it has two rays, resulting two rays, R1 and T1, which are the reflected rays, and T1 is a transmitted ray of that object. And that reflected ray, it can be a lightning ray for other object, then it has a reflected ray, transmitted ray, and it's continuous. Now I'll explain what are laws of reflection. As you studied in your childhood, every incident ray has reflected ray and transmitted ray. So as you can see here, I is the incident ray and R is the reflected ray, and the angle at which angle between the normal and the incident is the angle of incidence, and the angle between the normal and the reflected is the angle of reflection, and I is equals to R. And here here V is a view direction, view vector, and R is a reflection vector. Reflection vector is equals to v vector minus 2 into v dot n into n. Ray tracing. The maximum depth of the tree affects the handling of refraction. If we send another reflected ray from here, when do we stop? Two solutions: stop at the fixed depth or accumulate product of reflection coefficients, and stop when this product is too small. Now we'll discuss about refraction. Snell's law states that when a ray goes from environment where it is eta 1, the coefficient is eta 1, to the area where the environment where the coefficient is eta 2, then eta 1 of first or eta 1 eta I by eta t equal to eta r, that is equal to sine theta t by sine theta I, the angles, the angle of incidence and angle of transmission. Here t equals to sine theta m sine theta minus n cos theta t. From the, as shown in the figure, we can easily understand that. And m sine I and angle of incidence equals to m sine theta t m sine theta of I plus n cos angle of incidence I equals to n cos theta of I minus m sine theta of I. From that we can calculate what is m. When we substitute the m equation in the t, we'll get sine theta of t by sine theta of I into n cap of cos theta of I minus I cap minus cos theta of t into n cap. When we rearrange all the terms, we'll get and we also know from the figure that cos theta of I equal to n cap into I cap, and cos theta of t equal to 1 minus sine squared theta t. By substituting everything, we'll get t cap, that is transmitted ray equation. Converging lens and diverging lens. If a smooth surface replaces the prism, a well-defined focus produces a clear image. Diverging lens. The rays are diverged. What is focal length? The intersection of the point with the lens is called a focal length. The focal length f is positive for a real focus converging and negative for a virtual focus. The next topic is aliasing. Generic problem of raster graphics. What is aliasing? As you can see, the entire pixel can be only in one color. As you can see, the real object has a clear image differentiation, but when this image is represented in a pixel wise, we cannot get that difference because every pixel can have only one color. That is called aliasing. This is called jagged edges. We cannot get a real sense when we see in a picture. What is anti-aliasing? Anti-aliasing nothing but averaging the pixels so that there is not much differentiation between the pixels. So here are the references I have taken. Thank you.